let's get started with a bit of notebook 3. And this is a very exciting point, I think, for the activity because it's after the tools that we gathered with the help of Lord Drake of Aparajito and of Uboji. We can finally use Python as a tool for working on some astrophysics. So that's very exciting. So here in this activity, we will start constructing something that is often called a CMD, or a color magnitude diagram. So you will see often um, this acronym being thrown around. It is something that we will elaborate on during the activity, but it was discovered, or like maybe just first constructed by some astronomers during the 20th century, and it is a very key cornerstone of modern astrophysics because it started just like as a funny pattern that we could see if we organized two measurements that we could do from observing groups of stars into a very nice plot, and noticing that there was like patterns that told us something about the physics of the stars we were observing. So it is quite interesting tool. So we're gonna use here like just a group of stars. We have like a list of information and like different variables that were measured for this survey called Splash. And they're stars in the Andromeda galaxy. So that is like a very important first step to know what data set we're working with. And we're gonna start just first by importing our libraries, like the libraries that we're going to be using. So as mentioned before, we're going to be using NumPy, we're going to be using Matplotlib pyplot, and yeah, we're gonna just mostly focus on those two, which help us first store our data in arrays, and then that's going to be very efficient for manipulating the data, doing operations on it, and then plotting it nicely, as Boji was showing us using Matplotlib. So that's really fun. Um, I think Philip that designed this nice notebooks, he did it he did a very cool job of setting up first the environment of the plots that he wanted to build. So there is a couple of cells here at the beginning where he mentions these are his preferred settings, but these are not like mandatory cells. They just will make the rest of the job quicker for us and also have some aesthetic value to it. So for example, these first two is like if you're writing or like doing some document on PowerPoint or in Word, this is just setting the font and setting the font size of your plots. So this is going to be set for the rest of the plots that are generated after this cell. So then, oh, we have a, oh, I guess I didn't run the first one. Wait. So I love Python because it will tell you when you're messing up something and you have to go back and check if you actually ran things properly. So perfect. Okay, now we have our font size and our font defined. And then here we have a few commands that will, this is a function that has a few commands that will initialize the plots that we're going to generate. So we'll simply just create the canvas on which we're going to paint our beautiful color magnitude diagram. So feel free to just run it without paying too much attention to it. But if you want to look into each line, the first one that says F, just like this one just generates like a frame object, and this one will set the size of the figure, so you can constrain the dimensions of the figure that you want to make. This one will constrain the view that we have to a specific range of values in the x-axis, so that x-lim that Boji was mentioning. And then here, when we plot it, you'll notice something that Boji was mentioning that is very much useful in astronomy, and is that the limits in the y-axis are defined first with the bigger number 24 and then with the smaller number 18, because for some quantities in astronomy we like to flip the axis and like look at them the other way around. This is more thanks to tradition and how we measure the brightness of stars, but I'll mention a bit more about that later. And here we have just simply the two labels that we're going to talk about more in detail soon. So this is simply the function that will help us make our nice plots. And then here we have a function that also this one, I will not go into detail on it because it will take a lot of time to explain the logic behind it. This one is mostly just to make it quicker to choose a set of stars that we will pick from a set of conditions after we do the activity and simply save those stars into a separate document with the data extracted, So we have a catalog, that's what we call a catalog, that was taken with the telescope, and that just has like all of the stars available to us for this activity. And we're gonna separate different stars according to if they belong to different groups. So we can create a new catalog that comes from saving the stars that are part of each group taken from the bigger catalog. So that's kind of the idea. So I'm gonna stop to explain all this. This is just gonna be something that we will call to give it a name, set some parameters, and then it will just save a file for us into our folders. So now with everything all set after running those first few cells, we can go into extracting the data that we have in our catalog as a starting point, the big catalog. So this was taken together, combining data from the Keck Observatory, which is operated by the University of California in Santa Cruz. So that's pretty cool. And we have a very cool team of scientists that routinely do observations from there. And I want to stop to do a quick ad for the Shadow the Scientist program, which is really, really cool, which is why I'm here. Actually, I learned about this beautiful team and about the Python tutorials because I started attending the Shadow the Scientist program because I was just hyped up to check out how astronomers were observing the sky, and then these guys were like, yeah, we're gonna stream, like live stream an astronomer taking observations live from Hawaii, like from the peak of Mauna Kea, where the Keck Observatory is located. So that's pretty cool. And then it also has data from the Hubble Space Telescope. So we can navigate to see that we have like this data set. If you go to the home tab that opens when you run the Jupyter notebooks, and if you have downloaded and extracted the notebooks in your own machine, wherever you have them, for example, in my case, it's here in the documents folder, and then I have the SIP Python workshop also subfolder in it. There is this folder called data that will have the keck HST .txt. So this is a .txt file. Very often you will see that this kind of format is used for storing data. There is many others, but this is a conventional one for many things. And if you open that file, so just double click on it and it will open in a separate tab. It will let you see what are the values that are stored in different columns. So here, separated by spaces, we have first two comment lines. So they start with this hash, and that means that they are not going to be read by a Python program as information that is useful for the code. Is more useful for the user, is for the person that is writing code or reading the data to know what they are handling. Because imagine if you just didn't have this information, like if you just had like a string of numbers, as a human, like that really doesn't tell you anything. Like you really don't know what you're looking at. So we have this first two strings to keep some context on the document. So first two columns are going to be the right ascension and declination of the star. So this is just each row represents the information for a different star. And right ascension and declination are just the two main coordinates that astronomers use to locate a point on the sky. So you can look more into that if you're interested. It has to be defined in a specific way. And each star has their own right ascension and declination. We can think of it similarly as of if you're in a different point on Earth, you will have some unique coordinates assigned to your place. So I don't know, your house has a specific longitude and latitude that is assigned to it, or like your town, your city. So this is the same for stars. You can define a system that allows you with two angles to locate any star on the sky. Then we have other two angles, which are here called xi and eta. These two angles are not as universal as the right ascension and declination. They are proper of this specific catalog, and they are just two angles that will tell us how far away the star that we're working with is from the center of Andromeda, the galaxy. So apparently, as you observe on the sky, the telescope was pointing a certain angle, let's say in the X and the Y directions from the center of Andromeda. And that is how Xi and Eta are defined and saved into this. This will be useful for one of the following notebooks, not for this one, but it's good to have everything in the same catalog. And then we have two weirdly named columns that are just like a string of letters and numbers. And this is because these are just two Hubble filters. So these are simply in a specific kind of notation that the Hubble collaboration defined to know which filters they were working with when observing a specific target. And filters are simply that when you observe a star, you constrain the light of a specific color to be recorded. So if you change filters, it's like when you wear like these little 3D glasses that have like a blue filter, red filter. So that's like constraining the amount of colors that you can let pass through the lens. So that's what's happening with filters, and astronomical observatories will have many different filters. And if you get into astronomy, you'll see that that is actually huge um, a huge source of problems sometimes, because you need to standardize which filters you're working with, or each observatory has to design especially with space observatories, they end up designing their own specific filters that the community that works with the data coming from those observatories will be more familiarized with. So these are the kind of the stereotypical names for Hubble filters. They're usually F and then number and then W, I guess, because maybe this is because it's like the wide field camera 475. These are not random numbers. They're usually tied to the notion that physics uses to connect with color, which is wavelength. So in this case, this might be a wavelength of 475 nanometers, let's say, and this would be a wavelength of 814 nanometers, let's say. I am not exactly sure of this, but this is what I would say with my astronomer brain that is not used to working with these data sets. But yeah, maybe Boji, if you've worked more with Hubble data, maybe you can correct. But yeah, so then from Keck observations, the Keck Observatory, which is, as I was mentioning, in Hawaii, it's a ground-based observatory. It's not in space, it's in ground. It has a very cool instrument called a high-resolution spectrograph. And with a high-resolution spectrograph, you can, by a method that we will see tomorrow, you can measure exactly the velocity that a star is moving, if it's moving away or towards you. You can exactly, like with very high accuracy, how fast the star is moving. And we call that the radial velocity, and here is measured in kilometers per second. So this second to last column will show us what is the measured velocity that we see in each of these stars. And then the last column is just a really good practice in science, which is the error measurement on that velocity measurement. So that is simply how certain the instrument was of that measurement of the velocity of the star. It's like when you measure something, say with a ruler. So if you have like a ruler like this one, you will be sure of measuring something. Say if I measure something and it measures 2 centimeters, or like let's say if we have a more imperial units audience, if you measure it 1 inch, your ruler will have these tiny marks that will constrain how accurate, how certain you can be of that measurement. So that's what we call the error. So in this case, in any measurement that you make in science, it will be preferred if you can report how certain you are of the measurement that you're making, and that's this last column about the error. So yeah, now that I broke down this whole document, we can go back to the notebook 3, and we will go back to importing that .txt file that has the catalog, the Keck and Hubble catalog, and save it into a set of arrays. NumPy is very smart for this because it really has functions that can do everything. And in this case, we use this one that is called loadtxt. So since we're going to feed it a txt file, we can use np.loadtxt to generate an array from data stored in a txt file. In this case, we can also take more advantage of it and make it even more convenient by not just saving it to a single array, which will have like all of the columns and everything like as a single entity, but we can save it into, how many are these? 7? Yes, no, 8. 8 different arrays, which are the columns that are in our file. So remember that this file has right ascension, declination, blah, 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 all the way till the velocity error. We can tell NumPy, please, I'll give you this file, please save it into 8 different arrays. And then each of the arrays that I'm getting out of this, it corresponds with one of these columns. So that is very convenient because then we have a full column that is only right ascension, a full column that is only declination, and so on to the filter magnitudes that we have here and the velocities. Now, coming back a little bit into what I was mentioning of the filters of the Hubble telescope, or the filters of any telescope, the thing that the astronomers during the 20th century that I was mentioning that started making color magnitude diagrams found out is that if you measure the brightness of stars in different filters, you can play around and find out things about the stars just by doing that, just by observing them, how bright a star is in specific colors. So in this case, they defined the quantity that in astronomy is known as color. We will talk also more about this tomorrow. But as a summary, it's simply subtracting the brightness of a star into different bands is what we call it. So it's just different bands, which are ranges of wavelength where we let the camera store light from the target that we are observing. So the color is defined as just the subtraction between those two quantities, between those two brightnesses, or as are often called in astronomy, magnitudes. So that's why it's called the color magnitude diagram, because it's connected to the astronomical notion of brightness, which is measured in magnitudes. Magnitudes are a very funny quantity. So first, let's just run this. This line will only generate our arrays, as I was mentioning, and it will create a new array that is called color from subtracting the brightness of all the stars in each of the two bands from the Hubble spacecraft. So we run that one, and now we can just plot our color magnitude diagram. If we recall a little bit what Boji was teaching us, we can use matplotlib. This is done here with scatter, but this is just to not do it with plot and have all the dots connected with weird lines. Scatter does exactly works exactly the same, but it will simply not connect the dots with lines. But it's the same. You could do this with plot and simply explicitly tell the function to not connect the dots. But this is another way to do it. And then the two arrays that we're gonna plot is on the x-axis, we're gonna plot this color quantity that we define. And on the y-axis, we're gonna pick one of the two brightnesses, one of the two magnitudes, and we're just gonna plot that. So this is why it's called the color magnitude diagram, because on the x-axis you have color, on the y-axis you have magnitude. And we're gonna add some other parameters because, as Boji was telling us, we can define the color of the dots that we're plotting. Maybe we can choose the size of those dots. So that's what this s=3 function is doing. And yeah, here this edge colors is just telling us don't put like a boundary with the color around the dot markers that we're putting on the canvas. So if we run this, this first call of the initialize plot function is simply generating our canvas, and then this plt.scatter is populating it with all the dots from our arrays. So if we run that, Let's see if that works. It's taking a little while because maybe it's many plots, or maybe I don't know if I missed some. Let me check real quick. It's, maybe it's I have to add a show. Maybe that would be annoying.
The plt.show. Yeah.
Yeah.
Okay.
Let's see. Yeah. So depending on the version of your notebooks, the plt.show line might be needed or not. Like it's I've been growing up with Python and I've moved from needing it first, then not needing it. Now we need it again. So okay. um, Whatever works, you know? So now we have this, which is a color magnitude diagram. I want to move a little bit just to mention an example of a color magnitude diagram in like science that is very relevant. This is from the Gaia spacecraft that has been gathering data on millions of stars for the past like 10 years, I think, or more. And if you do the color
It's
from
over a
two different
billion
maps,
by now, by
it's
the way.
over a billion,
It's well,
exactly.
I mean this I think this is from DR3, right? Gaia
Yeah, this is the older
DR3.
one. This is
Yeah,
DR3, I
I
think. Yeah.
think this has over a billion
DR2,
stars. Yeah.
actually. Yeah.
Oh, DR2. Yeah, I think it is over a billion. Anyway, yeah.
Yeah. So this spacecraft is incredible because it has allowed us to measure the distance to, yeah, Spargito was mentioning billions of stars to incredible accuracy and really uh, um, very clearly find our place within our own galaxy. And that is a very cool result. And a very important central part of this was thanks to building diagrams like this one. It's often called the Hertzsprung-Russell diagram because these were two of the many astronomers that worked with this kind of data sets, but they were like the main ones to popularize it in the 20th century. But they didn't know exactly what was going on when you plot like just brightness here and then color on the x-axis. I mean, they found out later with other astronomers, but at the beginning it was just like, hey, if you draw a diagram like this, you get this interesting groupings in different regions of the diagram. So they started defining that stars, depending on different conditions, could fall within different areas of the diagram. And nowadays we know that this big thick part in the middle is called the main sequence. And it's, for example, where our sun is like where stars spend their more normal part of their life in, you know. And then you have other structures like what's known as the giant branch, which can be divided there into the asymptotic giant branch, or yeah, there's different categories that have been assigned because with the passing of time and more detailed studies on stellar astrophysics, we learned that the position in the color magnitude diagrams, it's totally connected to the evolution stage of the star. So that was a very powerful result uh, that we use routinely nowadays in astronomy. So if we come back to the one that we're doing, it will not look exactly the same because we are looking at a very specific population of stars coming from the Andromeda Galaxy. And also, it is with a very different instrument. So all of these factors into to make it not look the same. But even in this one, we can already recognize like there's like three different regions, right? Like we have like three different clusterings of stars in this catalog. So you have some group here to the left that is clearly separated from the others. And then here, there's not that much of a clear boundary, but you kind of notice that there is like a little gap here that is kind of curved, where there's like a thick cluster here in the center. And then there's like another group above that that is kind of more sparse. So we can assign those to, from what we know about stellar astrophysics, we can recognize astronomers that some of these are red giant branch stars, others are asymptotic giant branch, and then we also have the main sequence. So to start, we can use the tools of NumPy and Matplotlib to cut slices of these and visually separate them, and then also save them in different catalogs. Those are the catalogs I was mentioning earlier that we want to save them in. So we can start by recognizing that the left part is what we will define as the main sequence. The part here on the left, which is bluer stars. They are, as I was mentioning, in the main part of their life cycle. They are more conventional stars, let's say, quote unquote, while the ones to the right that are going to be redder stars are stars that are older, that are already in the final stages of their evolution as stars. So
So
we
the
can start by,
color,
yep.
so the color of a star, I mean, color in the colloquial sense, not the astronomical sense, but also color in the astronomical sense. Both of these things depend on the temperature of the star.
Yeah.
And like Hero showed you in the HR diagram, the color you can see is the label for the x-axis below, and for the x-axis above, the label is surface temperature. And that's basically, the temperature is basically what's reflected in the astronomical color, and also how you visually see the star. So cooler stars appear redder, and or rather stars with cooler surface temperatures appear redder.
Yes.
And stars with hotter surface temperatures appear whiter and bluer. And you can see that the other two axes are magnitude and luminosity. So magnitude is obviously, as Hero explained, what we see as the brightness, what we can observe. And luminosity is kind of what you calculate theoretically, because magnitude will depend on a few things, right? It will depend on how far away the star is. So that's apparent magnitude, but absolute magnitude is when you adjust for the distance. In our case, we assume the distance is more or less the exact same because the galaxy is so far away that the difference between the different parts of the galaxy barely matter. So we don't specify absolute magnitude or relative magnitude because, you know, it's all the same. It's all the same. But luminosity is basically what you can theoretically calculate, taking into account any gas and dust that might be between us and the star, obscuring some of the light that might affect the brightness. So luminosity is what it's actually like. That's what we are calculating. And surface temperature and luminosity are the two variables on a standard, HR diagram. But we are doing observational astrophysics here. So yeah, that's what Hero is taking through the color magnitude diagram. Sorry for the interjection, Hero.
No, perfect. Thank you. That is a lovely comment on the astrophysics of this, because it is really, really important, really interesting. Yeah, so we are here, focusing on the observational aspect, so we can measure how bright things look from Earth with our telescopes, and then to do the jump into how much power is being actually emitted on those stars. That requires other steps, and it's a different problem. But it is very important to make it, and that's how you make these kind of diagrams that are more precise and more informative, and will connect the information we observe from telescopes to actual surface temperatures on stars. To me, that's one of the most fascinating facts in astronomy, is that we are able to determine how hot a star is without having to go and plug a thermometer on its surface, because also that would be impossible. But even if we could reach a star, because that's it's impossible to reach it. Stars are into temperature levels that are hard to directly measure, and it's crazy that we can do that just with observational tools, just from hundreds or thousands of light years away. Okay, we have a couple more minutes, right, Jamika? I think almost done.
Yes, that's right.
Cool. So to constrain that, to draw those lines on the plot, we can start by first following. So this is what you will see if you run this notebook. We can start by drawing first the main sequence of this color magnitude diagram. So let's just run the cell as it is, and then we will fill up the rest very quickly. And also I have to add probably where, yeah, here where I'm plotting stuff, Plt.show. Very important. So you'll see that I managed to separate the part that I will call the main sequence and just color it differently than the rest of the group of stars. So this is very cool because of a property that we can use in Python, and is that we can take arrays and verify if a condition is satisfied, as we were seeing earlier with Apergito and with Boji and Ludwig. So we can check for the ones that have the color below 1.75, because that's just by eye. Like, you can try to calibrate it and change that value and see if something works better for you, like depending on where you can reach the right group of stars according to what you see visually on the diagram. And also you can limit the brightness to being higher than 23rd magnitude. Here, notice that I say like the magnitude will be lower than 23, but that means it's brighter stars. So since we have our axis flipped, we have to kind of flip our brains a little bit on that one and think, okay, I want to catch everything that is above this 23 line, and then everything here is going to be part of my main sequence, but that means it's going to be smaller because I'll be going to smaller numbers. So pay attention to that, because that's why this is why the y-axis array, the magnitude in the F814W filter, has to be smaller than 23. You can also, again, tweak that one and see if a different selection seems to work better for you. And then we just initialize another plot where we're gonna plot the same thing, but then on top of that, we're gonna add the selection of each of the arrays, color, the magnitude in the filter, that where only these conditions are satisfied. So if these conditions are satisfied, this MS array is going to be an array saying where it is true that happens, or where it is false. And then when you call that as the argument of another, or like as the index of another array, is going to only give you the places, or like the values of color, where MS is true. So where the main sequence is true. So we simply here also add plt.text. That's another useful, more visual command that just gives us the ability to put a text tag on somewhere on the plot. Here we give it this two coordinates just by eye, just so we have this MS written here. You can also play with those coordinates, move it around, and see if there's a different place where you would like it better. And then we will use the right catalog function. We'll simply call that function to save all of the arrays, the right ascension, the declination, xi, eta, the filters, all of it. So everything that we were mentioning before, but where the main sequence condition is true. So the stars that we tag as main sequence, all of their information is going to be saved in a different catalog that is going to be called mscatalog.txt. So we're simply saving it with a specific name. You could change this name to something different, but just to keep track of it and know that this is our main sequence catalog from this data. Since we know that, we're simply going to call it mscatalog.txt. And here we add also this line, because this function was written in a very smart way, where you can also keep track of what each of these quantities that you're saving means. So to do the other part of to separate the other part of the dataset, we will simply notice that here we have a curve that seems to be like the boundary between these other two groups. So we're going to define that curve, and just because that's how we work a lot of the times in science, we think of something that looks like a mathematical model that we know, and we try to apply that and see if it works. So a mathematical model that seems to work here, I would say, seems to be a parabola. So if we were to use like a parabola right here, we could maybe divide the two populations and use that as the condition on which we select the other two catalogs. So we can simply, I will do it very quickly. It says we can have the parabola equation, which is this one right here, and we can replace the numbers for things that would work. I had set aside some numbers that work, so I'm gonna just simply type them in, and you can play around also, because it doesn't mean that they are the correct ones. It's just that those seem to work for me, but check for yourself. So notice how this is the equation for a parabola or a quadratic equation. If we go to a graphing calculator and we type in that equation, so it's a, which is just one constant that you set, x minus h squared plus k. This h and k are offsets, so it will allow me to move right or left my parabola, and then the k one will be up or down. And then the A is going to help me modify the amplitude of the parabola. And I can make all of them like change with time. And then you have crazy parabolas that do funny dances. So if you want to play around with a model, like if you think something that you see in nature, in this case, in one of these data analysis activities, fits with a mathematical model that you want to fit to it, you can first write down the equation of the model that you're thinking of, and getting more familiar with it is very, very helpful. So here, like, oh, if I change this parameter like this, what does it mean for the distribution that I'm showing? So here, that's why we use this equation. And what we do is, okay, let's see where the brightness, so the brightness of the y value is higher than the parabola. So what that means is, since it's going to be higher, it will be down, since our y-axis is flipped. So we're going to select everything that is under the parabola in this case. And then also we need to separate it from the main sequence. And remember that we selected the main sequence to be under, so to the left of 1.75 value in color. So I will select the rest. So it's like to the right 1.75. And we can add that to the plot. That should be easy enough if we simply copy how we plotted also the, maybe I can take away the show, because I will do that on the same plot. So we can add that to the plot simply by replacing. So this one we don't need because we already plotted all of the catalog. And this one, instead of MS, we will switch that for RGB, because those are the stars that now we are plotting. RGB, yes. And we can switch the color to differentiate it from the MS to green. And now we also want a tag that says that those are the RGB stars, but I'm gonna move it, I don't know, somewhere more to the right, let's say 6. I don't know, let's try if we keep it there, how it looks like. So now look that our boundary is more noticeable here, the ones that are now green that were before gray, and they got the tag RGB, which got put in blue. I'll switch it to green just to be more consistent. And then we can do exactly the same with the AGB stars, which are the ones that are left, the ones that are up here, but simply by flipping the condition that we set. So it's also going to be to the right of 1.75, but now it's going to be under, like, or above in this case, the parabola. So it's going to be a lower magnitude for that. And if everything looks right, let me check. So let's say, let's keep these ones green now that I think of it, the AGB ones, and these ones, because they're the red giant branch, let's make them red. I think that would make more sense. Red. So yeah, so we set the condition here, and now we're gonna call that AGB, not RGB, but now AGB, asymptotic giant branch. And then we're gonna switch where it says RGB for AGB, AGB, and this one I'm gonna have to put maybe higher up. let's say 19 or something. Maybe should work. That's green. I think everything looks good there. And now we're gonna just delete this show so we show it at the very end. And we're almost done. Nice. So now you see that we have split our three populations within the group of stars that we're observing in our catalog. This is only separated visually in the plot. We have to save the other two catalogs. So notice that we called here the write catalog function for the main sequence. We can simply just copy that and just put it under the RGBs, for example. Simply make note of calling it something like RGB catalog. And then the data sets that we're saving is where the write ascension is RGB, the declination is for the RGB, and so on and so forth. You will simply replace that in all of the indexes of all the arrays. And that's simply how you would do it. Sometimes it gets a bit tedious if you have many arrays, but you can also automate that with other smart Python tricks. So this one, let's just sanity check it. We're going to save it on the RGB catalog.txt, and each of the arrays that I'm saving in that catalog are the ones where the RGB condition will be set to true. So wherever RGB condition is true, it's going to save a value for all of the variables that we have for each of the stars. So that ensures that we're only keeping track of the stars that we care for that specific population. So we can go ahead again and copy that and do the same for the AGB stars. So in this case, AGB to the plot, and then we can write the AGB catalog. So we simply switch, in this case, the R's for A's, and that's going to be easy enough. And that's also the good part of writing organized code where you're keeping track of the names of things. It becomes more comfortable, and if code gets messy, it is really a pain to catch errors. When your code is more organized, it's a bit easier to catch errors. Check if everything is working properly. And no errors here, so that's good. So we have visual confirmation of what we did, and also whatever is saved here in blue is saved also in a new file called main sequence. And whatever saved here in green is on the AGB file, and the red is for the RGB file. And that is lovely. And also we can simply run these other two lines that will tell us more informatively how many stars did we actually find in each of these populations. So we can just check the length of any of these arrays from the original arrays, from the original catalog, and that will give us the number of stars. And then we can simply sum the amount of stars in each of the condition arrays, or like the tag arrays that we call main sequence RGB, AGB, and divide it by the total amount of stars, and then we get the fraction. And then we'll see that if we do the union of those sets, we'll find how many we actually selected, and because there's going to be some that just didn't make the cut for any of the filters. So those ones, it's also useful to keep track if you're having any like leftover stars that maybe are falling out of your selection criteria, and it's also relevant. So we also write here like which ones were not selected. This little squiggly line is the not operator. So we'll do the opposite of the selected, so the not selected, over the total amount of stars. And this is simply going to print how many stars we have in each of the categories. So we have fraction of the main sequence is about 15% of the total catalog. RGB is about 55% almost of the total catalog. AGB is 14%, and then we just did not select about 16% of the population. So that's it for now for notebook 3. Make sure that you can follow along and go over it a couple of times. Make sure to play around with the conditions that you put here on the quadratic model. Maybe even think if there is something better than a quadratic model to fit this little gap right here. Like what happens if you do cubic? What happens if you do other kinds of curves that you know about from your maths learning? and that might help you catch different amounts of stars into different populations or different categories. So yeah, that's it for now. Keep your catalogs handy because they're going to be useful for I think for the final notebook tomorrow.
That's right.
And yeah, and that's it for me.